America has always been a country of experiments. That's basically what it was from the beginning, an experiment in whether a new kind of country could work. But what I want to talk to you about today are different kinds of experiments, the ones that happened in mountains and caves and in the sky above your head, without you knowing about it, the ones that started in garages and classrooms and ended up in every home on Earth. America's scientific history is one of the most extraordinary stories ever told, and most of it never made it into the textbooks. Over the next hour, I'm going to take you through 8 hidden chapters of American science history, stories about experiments so unusual they seem like science fiction, about discoveries that happened in completely unexpected places, about inventors and scientists who were told they were wrong and turned out to be the most right people who ever lived. All of it real, all of it happened, all of it in America. Let's start underground. Chapter 1. The lab built inside a mountain. In the Black Hills of South Dakota, about a mile underground, there is a science laboratory. Not a small one, a massive one. With miles of tunnels, multiple levels, advanced equipment, and a team of scientists working on some of the biggest questions in physics. It's called the Sanford Underground Research Facility. And the reason it's a mile underground is fascinating. Scientists studying the fundamental particles of the universe, the building blocks of everything, face a constant problem. The surface of the Earth is noisy, not loud, not literally noisy, but noisy with particles. Cosmic rays, high-energy particles raining down from space, constantly bombard the Earth's surface, and for certain experiments that require detecting extremely rare, extremely tiny particles, that cosmic noise drowns out the signal completely. It's like trying to hear a single whisper in the middle of a rock concert. You need to get away from the noise, and the best way to get away from cosmic ray noise is to go underground, deep underground, where the rock above you filters out the cosmic bombardment and leaves a much quieter particle environment. The facility in South Dakota was built in what was once the deepest gold mine in the Western Hemisphere, the Homestake Mine. It had been operating since 1876. It produced 40 million ounces of gold over its history, and then the gold ran out and the mine closed in 2002. At which point scientists said, "Wait, don't fill it in. We can use this." And so a gold mine became a physics laboratory. 1 mile underground. One of the most important experiments ever conducted there was the search for neutrinos. Neutrinos are fundamental particles, tiny, almost massless, with almost no charge, that pass through ordinary matter almost without any interaction at all. Right now, trillions of neutrinos from the sun are passing through your body, every second, without you feeling a single one, without any of them stopping. Neutrinos pass through the entire Earth like it isn't there. For decades, scientists were unable to detect them because they interact with other matter so rarely and so briefly. Then physicist Ray Davis had an idea. He placed a tank containing 100,000 gallons of cleaning fluid, dry cleaning fluid, the kind used in laundry, deep inside the Homestake Mine. The idea was that very occasionally, incredibly rarely, a neutrino from the sun would interact with a chlorine atom in the fluid and leave a tiny, detectable trace. It was an almost impossible experiment. He was looking for a signal so faint that even a single cosmic ray interaction could produce a false positive. That's why it had to be a mile underground, away from the noise. Over the course of several decades, Ray Davis detected solar neutrinos for the first time in history. But here's the wild part. He detected fewer than the theoretical models predicted. Far fewer. Too few. For years, this was called the solar neutrino problem. Scientists argued about it endlessly. Either the models of how the sun works were wrong, or the experiment was wrong, or something else was going on. What was actually going on was far more exciting than either of those options. Neutrinos were changing form. They were oscillating, transforming between different types of neutrinos during their journey from the sun to Earth. The detectors could only catch one type. The others were passing right through. This discovery, called neutrino oscillation, completely changed our understanding of particle physics. It proved that neutrinos have mass, which the standard model of physics had assumed they didn't. Ray Davis won the Nobel Prize in Physics in 2002 for his work on solar neutrinos. The experiment he ran in a gold mine with a tank of dry cleaning fluid changed our fundamental understanding of the universe. A mile underground, in South Dakota, where people used to mine gold, science finds its way into the most unexpected places. Chapter 2. The Town That Caught the Sun. In 1979, in a small town in Massachusetts called Carlisle, something strange began to happen. House by house, roof by roof, the town started going solar. Not because the government told them to, not because of a corporate program, not even because of any organized movement. Because of a science project. One that a local scientist had started in his own home, that his neighbors noticed and copied, and their neighbors copied, and their neighbors' neighbors copied. Until Carlisle, Massachusetts had one of the highest concentrations of solar-powered homes in the entire United States. The scientist was a man named Steve Connors. In the late 1970s, during the energy crisis, when gas prices were through the roof and America was desperately searching for alternative energy sources, Connors decided to test whether a regular suburban home could run primarily on solar power, not a specially designed experimental facility, his own house. He covered his roof with solar panels, insulated the walls to hold heat, installed passive solar windows that let in winter sun and blocked summer sun. He documented everything. His neighbors could see the panels on the roof. They asked about it. He showed them the data. And one by one, they started doing the same thing. What happened in Carlisle is now studied by sociologists and environmental scientists as a case study in what they call social diffusion of innovation. The idea that technology spreads not just through advertising and corporations, but through neighbors watching neighbors, through trust, through curiosity, through someone seeing something work and thinking, I could do that too. But the deeper hidden science story here goes back much further than 1979. In 1839, over 180 years ago, a 19-year-old French physicist named Alexandre Edmond Becquerel was experimenting with electrochemical cells in his father's laboratory. He noticed that when he shone light on certain materials submerged in solution, they produced a small electric current. He called it the photovoltaic effect. Photo, from light. Voltaic, producing voltage. Light, producing electricity. He published his finding. And nobody paid much attention for about 100 years. In 1954, scientists at Bell Laboratories in New Jersey created the first practical solar cell. It converted about 6% of the sunlight that hit it into electricity. The New York Times called it the beginning of a new era. Within 4 years, The first solar-powered satellite, Vanguard 1, was launched into orbit. It's still up there today, the oldest man-made object in space, still generating a tiny amount of power from the sun's rays. From Becquerel's Curiosity in 1839 to Vanguard 1 in 1958 to the rooftops of Carlisle in 1979 to the solar panels on millions of homes today. A line of discovery stretching nearly 200 years, starting with a teenager noticing something in his father's lab, asking why, and pulling on the thread. Today, solar power is the fastest-growing energy source in the world. All of it traces back to a 19-year-old who noticed something strange happening when light hit a piece of metal in water and wrote it down. Science spreads the same way every good idea spreads. One curious person at a time. Chapter 3. The teenage inventor Edison called a genius. In 1921, a 14-year-old boy in Idaho was plowing a potato field with a horse. His name was Philo Farnsworth. And while he was plowing, going back and forth in long parallel lines across the field, he looked down at the rows he had just cut in the soil. And he had a thought. What if you could capture an image the same way? Scan it line by line, row by row, back and forth. Not with film, not with chemicals, with electricity, with electrons. What if you could broadcast a moving picture through the air, the way radio broadcasts sound? Philo Farnsworth was 14 years old. He was homeschooled, no formal science training. He lived on a farm in rural Idaho with no electricity for much of his childhood. He read science magazines by kerosene lamp. He thought about electricity constantly. By the time he was 16, he had sketched out the complete theoretical design for an all-electronic television system. He showed it to his high school science teacher. The teacher was so astonished that he carefully preserved the drawing, recognizing that he was looking at something extraordinary. At the age of 21, Philo Farnsworth demonstrated the first all-electronic television transmission in history on September 7, 1927, in a small lab in San Francisco. The image he transmitted was a simple straight line, a single horizontal line of light. But it moved. It changed. It was transmitted electronically from one room to another without any film, any mechanical disc, or any other physical medium. It was a complete revolution in human communication. Born in the mind of a 14-year-old plowing a potato field. Thomas Edison, who was in his 80s at the time and had met and assessed hundreds of inventors, was asked about Farnsworth. He said Farnsworth was one of the most remarkable inventors he had ever encountered. But here is the hidden science story. Philo Farnsworth's invention, the one he had designed as a teenager and patented as a young man, was immediately contested by one of the most powerful corporations in America. RCA, the Radio Corporation of America, had its own television research program. Their chairman offered Farnsworth $100,000 for his patents. Farnsworth refused. He knew what he had. RCA sued him instead, claiming their own patents predated his. The legal battle lasted for years, and then Farnsworth's high school science teacher produced that drawing, the one he had carefully saved, dated years before RCA's earliest patents. Philo Farnsworth won. He died in 1971. His face has never appeared on a stamp. His name is not in most history textbooks. Most people who watch television today have never heard of him. Every television set ever made, every screen you have ever watched, every streaming video, every YouTube video, including this one. All of it traces back to a line of plowed earth in an Idaho potato field, and a 14-year-old who asked, "What if you could transmit a picture the way a field is plowed? Row by row, line by line." Science doesn't care how old you are, or where you grew up, or whether you have a fancy laboratory. It just cares whether you keep asking why. Chapter 4. Project Echo, the balloon that talked. In 1960, NASA launched a balloon into space. Not a small balloon, a 100-foot diameter balloon, made of a thin metallic material called mylar, and inflated in orbit until it was roughly the size of a 10-story building. The balloon was called Echo 1, and it was one of the most brilliant pieces of engineering simplicity in the entire history of the space program. In 1960, satellite technology was in its infancy. Complex electronics in orbit were expensive, unreliable, and extremely difficult to repair if something went wrong. So an engineer at NASA named William O. Sullivan Jr. asked a different question. Instead of building a complex electronic relay satellite to bounce radio signals around the Earth, what if you just put a giant mirror in space? A smooth, reflective surface that would bounce radio signals back to Earth the same way a mirror bounces light. No electronics, no circuits, nothing that could break. Just a shiny balloon. It worked perfectly. On August 12, 1960, Echo 1 was launched and inflated in orbit at about 1,000 miles altitude. The first message ever bounced off an orbiting satellite was a recorded voice message from President Eisenhower. Transmitted from New Jersey, bounced off the giant silver balloon in space, and received in California. A human voice bounced off a balloon in space for the first time in history. You could see Echo 1 from the ground with the naked eye. It was the third brightest object in the night sky. Millions of people around the world looked up and saw it drifting overhead, a shiny dot moving silently across the stars, not knowing they were watching the birth of satellite communication. But here is the hidden science story that most people don't know. The data collected from Echo 1 and its successor, Echo 2, gave scientists something they had never had before: precise measurements of the density of the upper atmosphere and the exact shape of Earth's gravitational field. It turns out Earth is not a perfect sphere. It's slightly flattened at the poles, bulging at the equator, and has subtle gravitational variations caused by the uneven distribution of mass inside the planet. Scientists knew this theoretically, but Echo's orbit, tracked precisely over months, gave them actual measurements. A map of Earth's gravitational field. That map is now the foundation of the GPS system that guides your phone. Every time you use navigation on a device, every time you type in an address and get turn-by-turn directions, the GPS satellites above you are constantly compensating for Earth's gravitational variations. Variations that were first mapped precisely because of a giant mylar balloon that William O. Sullivan sent into space in 1960. GPS, satellite internet, satellite television, modern weather forecasting, global navigation for ships and planes. All of it required knowing the exact shape of Earth's gravitational field. All of it traces back to a balloon. The most elegant solutions in science are often the simplest ones, and the people who come up with them are usually the ones not afraid to ask an obvious question. that everyone else has decided isn't worth asking. William O'Sullivan asked, "Why does a satellite have to be complicated? What if it's just a mirror?" Simple question. 60 years of consequences. Chapter 5. The Cave Bacteria That Changed Medicine. In 1986, a microbiologist named Hazel Barton was exploring a cave system in Lechuguilla, New Mexico. She was several hundred feet underground, in a cave that had been completely isolated from the surface for millions of years. No light, no connection to the outside world, no nutrients washing in from above. A totally sealed environment. And growing on the cave walls was bacteria, living organisms, thriving in conditions that should have been impossible to support life. How? The cave bacteria were eating rock. Specifically, they were breaking down sulfuric minerals in the cave walls and extracting energy from the chemical reactions. No sunlight, no photosynthesis, no food chain originating at the surface. Pure chemistry, life running entirely on rock-eating chemistry. These bacteria were the first strong evidence that life could exist, could thrive, in conditions completely isolated from sunlight. This discovery had two enormous implications. The first was for the search for life in space. Until Lechuguilla, most scientists assumed that all life chains eventually trace back to photosynthesis. If life can thrive in a completely sealed, lightless cave system running entirely on chemistry, then life could potentially exist in the subsurface oceans of Jupiter's moon Europa, or under the ice of Saturn's moon Enceladus, or in the deep rock of Mars. Caves on Earth changed how we look for life in space. The second implication was for medicine. Bacteria isolated for millions of years from the surface of the Earth had no exposure to modern antibiotics. They had been developing their own chemical warfare, their own biological weapons to fight each other, in total isolation, which meant they might contain compounds that nothing on the surface had ever seen, compounds that modern bacteria had no resistance to, compounds that could become the next generation of antibiotics. Antibiotic resistance, the growing ability of bacteria to resist the medicines we use to fight infection, is one of the most serious medical challenges facing humanity today. Finding new compounds that bacteria have never encountered before is one of the most promising ways to stay ahead of it. And one of the best places to find those compounds is in the most isolated places on Earth. The deepest caves, the hottest volcanic vents, the most acidic lakes, the coldest ice sheets, the extreme places we barely explore. The solution to one of the biggest medical challenges of the 21st century might be living in a cave, right now, eating rock, waiting to be found. Which means the cave explorers, the people brave and curious enough to go into the dark underground places most people never visit, are doing some of the most important science happening anywhere on Earth. Chapter 6. The Cloud Seeders. On November 13th, 1946, a scientist named Vincent Schaefer climbed into a small plane over Mount Greylock in Massachusetts. He was carrying a container of dry ice, frozen carbon dioxide. And as the plane flew through a cold cloud, he dropped the dry ice into it. Within seconds, the cloud began to snow. For the first time in recorded history, a human being had made it snow, on purpose. This was the birth of cloud seeding, the science of artificially inducing precipitation, and the story of how it happened is one of the most wonderfully accidental discoveries in American science history. Vincent Schaefer worked at the General Electric Research Laboratory in Schenectady, New York, under physicist Irving Langmuir, one of the most decorated scientists in America. They were studying supercooled clouds, clouds made of tiny water droplets at temperatures below freezing that somehow hadn't turned to ice. Schaefer was experimenting in a home freezer he had lined with black velvet to see ice crystal patterns more clearly. He breathed into it and watched the crystals form. One hot summer day, the freezer wasn't cold enough, so he dropped a chunk of dry ice in to cool it down. The moment the dry ice hit the supercooled air, millions of tiny ice crystals formed instantly. Schaefer understood immediately what he had seen. If you could introduce a nucleating agent, something for water droplets to crystallize around, into a supercooled cloud, you could trigger precipitation. You could make it rain or snow. You could change the weather. 3 months later, he was in that plane over Mount Greylock. And it worked. Cloud seeding has been used ever since for drought relief, to increase snowpack in mountain ranges that supply drinking water, to reduce the size of hailstorms before they hit crops. China used cloud seeding before the 2008 Beijing Olympics to try to ensure clear skies for the ceremonies. The American West uses cloud seeding programs in mountain ranges to supplement snowpack that feeds rivers and reservoirs. But here is the hidden science story that most people don't know. The same research program that produced cloud seeding also inspired something that still affects weather forecasting today. Langmuir and Schaefer worked with a colleague named Bernard Vonnegut, the brother of the famous novelist Kurt Vonnegut, who discovered that silver iodide crystals were even more effective at seeding clouds than dry ice. The crystal structure of silver iodide is almost identical to the crystal structure of ice. When you spray silver iodide into a supercooled cloud, water molecules can't tell the difference. They start crystallizing around the silver iodide particles exactly as they would around ice. The discovery of exactly why this works, the precise molecular matching of crystal structures, contributed to a much deeper understanding of nucleation chemistry, which is the science of how things crystallize, which turns out to have applications in everything, from pharmaceuticals to materials science to the manufacturing of computer chips. One experiment, on a cold November day over Massachusetts, dropping dry ice from an airplane. And 80 years of science branching in every direction from that single moment. Schaefer didn't set out to change materials science or pharmaceutical manufacturing. He set out to understand clouds. Every great discovery begins that way, with someone simply trying to understand one small piece of the world and finding that the thread never ends. Chapter 7. The Blind Scientist Who Saw More Than Everyone Else. Gerard Vermeij has been blind since he was 3 years old. He is also one of the most accomplished evolutionary biologists and paleontologists in the world. Vermeij was born in the Netherlands in 1946. He lost his sight to glaucoma as a very young child. When he moved to the United States as a boy, he discovered the ocean and the shells. He would walk along the beach and pick up shells, hold them, feel them, run his fingers along their ridges and spirals and surfaces, and notice things that sighted scientists had missed for 100 years, because they were looking. When you look at a shell, you see it. When you feel a shell, when it is the primary way you experience the world, you understand it differently. You notice things with your fingertips that eyes simply glide over. Vermeij noticed that shells in the Pacific Ocean felt different from shells in the Atlantic. Thicker, more elaborate, more armored, more defended. He began to ask why. His answer led to one of the most important theories in evolutionary biology, a theory he called escalation. The idea that the evolutionary arms race between predators and prey is the primary driver of the increasing complexity of life over time. Here's how it works. A predator, say a crab, evolves stronger claws. The snails it preys on respond by evolving thicker shells. The crabs respond by evolving even stronger claws. The snails respond with even thicker shells, back and forth, each side escalating. And over millions of years, this arms race drives both species toward greater and greater complexity. Vermeer could feel this history in the shells. The Pacific has more predators than the Atlantic. More predators equals more evolutionary pressure. More pressure equals more defense. More defense means thicker, more elaborate, more complex shells. His fingers told him the story of millions of years of evolutionary history by simply picking up shells on a beach and paying attention. Vermeer became a professor at UC Davis. He has published hundreds of scientific papers, written multiple books, won a MacArthur Fellowship, sometimes called the Genius Grant. He does his fieldwork by feel, wading into tidal pools, reaching into crevices, identifying organisms by touch alone. He has described species no sighted scientist had ever noticed, despite hundreds of years of people walking those same beaches and looking at those same shells, not because they weren't looking, but because they were only looking. Vermeer's story is a hidden science story in a different sense than the others I've told you. It's not hidden because it was classified, or because it happened underground. It's hidden because it challenges a fundamental assumption most of us make about how science gets done. We assume science requires seeing, observing with your eyes, reading instruments, looking through microscopes and telescopes. Vermeer's career is proof that observation, real, deep, careful, attentive observation, can be done in ways we never expected. And perhaps more importantly, the things we haven't noticed yet aren't necessarily invisible. They might just be waiting for someone who pays attention differently. Science needs every kind of mind, every kind of perception, every kind of way of being in the world, because the universe is complicated, and it will take all of us paying attention in every different way we know how to understand it. Chapter 8. The first computer bug was an actual bug. I want to end with a story that is both true and one of the best things I have ever discovered. On September 9th, 1947, a team of engineers was working on a massive computer called the Harvard Mark II at Harvard University. The computer had stopped working. The engineers checked the circuits, checked the connections, checked the relays, and they found the problem. A moth. A real moth had flown into the computer, gotten stuck between the contacts of a relay, and caused a short circuit. The engineers removed the moth, taped it into the logbook, and wrote next to it, "First actual case of bug being found." And that is why we call computer errors bugs, not metaphorically, not as an analogy, because on a specific day in September 1947, an actual insect caused an actual computer error, and the engineers who found it were clever enough to realize they had just named something. But here's the hidden science story that makes this even better. The engineer who wrote that logbook entry was not just any engineer. It was Grace Hopper. and Grace Hopper changed computing more profoundly than almost anyone else in the history of the field. Grace Hopper was a mathematician who joined the Navy during World War II and became one of the first programmers of early computers. She was brilliant, creative, and relentless, and she had a problem with the computers of her time. Early computers were programmed in what's called machine code, pure numerical instructions that told the computer exactly what to do at a mechanical level. To program a computer, you had to understand the specific architecture of that specific machine. You had to speak the computer's language every single time, for every single task. Grace Hopper thought this was backwards. She said, "Why can't the computer learn to understand human language? Why do humans have to translate everything into machine instructions? Why can't we build a translator program? A program that converts human-readable instructions into machine code automatically?" Everyone told her it was impossible. Computers can only do arithmetic, they said. They can't understand language. She built it anyway. In 1952, Grace Hopper created the first compiler, a program that translates human-readable code into machine instructions automatically. This was the most important development in the history of computing after the invention of the computer itself. Before the compiler, programming was an incredibly specialized skill. After the compiler, anyone who could learn a programming language could write programs. Every app on your phone, every website you've ever visited, every video game you've ever played, every piece of software anywhere in the world. All of it was written in a programming language that compiles down to machine code. All of it was made possible by Grace Hopper asking a question everyone said was unanswerable. She rose to the rank of Rear Admiral in the Navy, one of the first women to do so. She kept working on computing until she was 79 years old. She received the Presidential Medal of Freedom in 2016, the same year as Margaret Hamilton from our first video. 2 women, 2 medals, 2 discoveries that quite literally power the modern world. And both of their stories start with someone asking, "Why do we do it this way? Is there a better way? What happens if I try?" The moth in Grace Hopper's logbook is preserved today at the National Museum of American History in Washington, D.C. The first bug, found by one of the most important scientists in computing history, on a September morning in 1947. The smallest things sometimes mark the beginning of the biggest stories. Pay attention to all of it. You never know which one is going to change the world. In closing, 8 stories. A physics laboratory built inside a former gold mine in South Dakota that helped us understand the fundamental particles of the universe. A town in Massachusetts where neighbors watched each other's rooftops and sparked a solar revolution that's still growing today. A 14-year-old in Idaho plowing a potato field who invented television and never got the credit he deserved. A giant mylar balloon in space that accidentally mapped Earth's gravity and made GPS possible. Cave bacteria in New Mexico that had been eating rock for millions of years in total isolation and might hold the key to the next generation of life-saving medicine. A scientist who dropped dry ice from an airplane and made it snow on purpose for the first time in human history. A blind biologist who read the evolutionary history of life on Earth through his fingertips. And a moth in a logbook, found by one of the most important computer scientists who ever lived, that gave us a word we still use every day. None of these people set out to change the world. They set out to understand one small part of it. They asked a question. They pulled on a thread. They noticed something. They refused to accept that something was impossible. And the world was never quite the same. America's scientific history is one of the greatest adventure stories ever told. And we've only scratched the surface. The best discoveries, the ones that will change everything we know, haven't been made yet. They're waiting for whoever is curious enough to look. That might be you. Actually, it definitely could be you. Subscribe for more hidden history, new stories every week. See you next time.